Hi. So as said, my name's Tom, and I'm currently a postdoc at the University of Exeter, but I'm going to talk today about some work that I did during the first part of my PhD at the University in Amsterdam, the Free University of Amsterdam, in collaboration with Charles Darwin University in Northern Australia. And this is about a problem that was quite neatly framed by Anil in the first talk when he looked at his life maps, is that how do you connect often very sparse ground truth observations to larger scale satellite observations, and can you make something useful, some sort of mapping product out of that? And we did this in the context of wildfire emissions. So we were trying to look at how to constrain savanna burning emissions in the southern African savannas. And for that you need to know four things. You need to know the burned area, so BA, and we can do that fairly well through just multispectral imaging from MODIS in some cases, but also Sentinel-2 for higher resolution products. We need the fuel load, which is what I'm going to be talking about in this talk. So biomass in different categories, which parts of those savannas burn, the grasses or the trees or the shrubs. We need to know the combustion completeness of those. I'm not going to talk about that because that's a whole can of worms that I don't want to go into today. And we need to know the emission factor, so how many kilograms, say, of carbon dioxide is emitted per kilogram of dry matter fuel burned. Now we're getting better at the burned area. We've got great satellites, great algorithms that can map surface cover changes. We're getting much better at emission factors through work that's done by my colleague in Wageningen in the Netherlands, and other people as well. But our biomass maps, so large-scale biomass maps, are largely limited to standing vegetation. So that's using things like synthetic aperture radar to measure backscatter and infer canopy structure and biomass from that. Now that's great, but most savanna fires don't burn trees. And these are all pictures that I've taken from various parts of southern Africa, from fires, I think, in Botswana, or the top two in the middle, Mozambique on the bottom, and Zambia. And as you can probably see, like, some of them are quite big, but a lot of the standing vegetation doesn't get consumed. So if we want to really understand where these emissions are coming from, we need to understand the surface layers, and that's currently not really captured in our biomass maps. So we did a lot of field measurements. We went into forestry and national park reserves, all these different locations across the continent, and also a few in northern Australia, although I haven't included these here on this slide. And we put in several plots across a number of years across the dry season. So I think the blue ones are sort of early-ish in the dry season, so probably more moisture content in the fuel, and the red ones are later on in the dry season, where you'd expect in most places that especially the grass layers, etc., have dried out. And we tried to spread these plots across a rainfall gradient, so we had a couple in the more arid areas in the south, and as you go more towards the northeast, you get more and more rainfall, and hopefully that's captured in so that means that you've captured a good sample of plots in your survey. And each one of these plots had 2 or 3 transects in them. And in these transects we took measurements of 4 or 5 different fuel categories. And the relevant ones for this survey are the surface fuel. So that's things like grass, which we measured in the blue 1 by 1 meter squares at 5 separate intervals along a 50-meter transect line. Also in those blue squares, we took measurements of surface litter, so that's dead material, leaf litter, any woody material that is smaller than about 5 millimeters in diameter. And in the larger red squares, we looked at coarse woody debris, so that's anything bigger than 5 millimeters in diameter, but smaller than 5 centimeters. There's obviously a couple of other classes, like more larger dead woody material or shrubs and things, and we did look at those, but that's not included in the rest of this talk, so I won't go into them here. And at each one of these survey sites, we flew a drone with a multispectral camera attached to it. And in each one of these orthomosaics, shown on the right here, that we built from all the hundreds of photos that we took from this drone, we could isolate these transects in that photo. That's what you see here, that, this colored in area, which represents a classification map based off of these drone surveys. So I'll go in the next slide, I'll show you what that means. But additionally, we also collected a lot of meteorological history from the plot site. So these areas burn frequently, so we said, okay, well, how much rain has fallen since the last time this place was burnt or disturbed in any way? What's the average solar radiation bin? Things like this. And using that, we had the ground truth data from our biomass measurements going in and weighing the fuels. Then a number of features from the drone maps, so the spectral reflectance in a couple of different bands, but also classification map and the meteorological data that I just mentioned. And that we could use as a set of features to train a machine learning model. I'm getting slightly ahead of myself. So this is what these separate layers looks like. So on the top left, going to go clockwise, is the true color image with one transect highlighted in red. There are 3 transects in this image. I'm just showing one. Then we have vegetation indices. So for example, the NDVI we used, but we weren't limited to that. We also looked at things like the leaf chlorophyll index and some water content related indices. Then following on from that is the classification map, split into 5 categories. So you either had a bare soil, so no vegetation cover, grass cover, foliage, so that's anything from small shrubs to large trees, woody material that was identifiable from the drone, and usually that is the either larger dead wood on the ground or deciduous trees. And then finally a shadows category where the area was too shaded for us to do anything with that part of the image. The bottom left one is the canopy height map that we built from photogrammetry from the drone, so that we also fed into that to see roughly what sort of... essentially we used it to split, okay, where are our trees, where are our shrubs? And using all of that information, all of those features, we could build a drone-based biomass map for an area of this size. So we did that using a random forest model, and I'll show some more information about that in the next slide, but we could split that drone biomass map into Sentinel-2 grid cells. And that each one of these red boxes is one Sentinel-2 grid cell. And that's a really effective way of taking a really sparse sample set, so in this case 3 data points, and creating a lot of extra sample points, so upwards of 40 in just one plot. And in this way, we can get from about 200 ground sample measurements to upwards of 4,500 data points, which is really useful for training a machine learning model, which is what we did then. So we trained 2 separate machine learning models, 2 separate random forests, one on the biomass measurements and drone data that we had, so that's including all of the meteorological measurements and everything, and then a separate one on Sentinel-2 data, and that was only based off of reflectance values, so 3 spectral bands and 1 land cover classifier. And the results look a bit like this, and I think honestly we were quite surprised at how well it all fit, especially for what you might call the more continuous surfaces, continuous fuel classes, so grasses and litter. And we ended up combining grass and litter into one total fine fuel class, as we found that actually made things a little better and more simple for us. Yeah, and in both the drone map and the eventual Sentinel-2 machine learning model, we found that for total fine fuel for the continuous surface cover classes, it actually did pretty well. And we ended up with errors of about just under 30%, which, considering you're getting a a biomass measurement on a 20-meter grid cell we thought was pretty good. We did look at other classes, you see coarse woody debris and shrubs, and we found that was a lot harder to do. And you really needed, then you really did need things like synthetic aperture radar to get a better idea of the structure of the vegetation to be able to have an accurate constraint on what the biomass for that area was. Most of the variation in biomass in our machine learning model from the drone side of things was explained by meteorological factors, which in the end wasn't so much of a surprise when you think about how frequent burning is in these places. So if we have one area that's burnt every 2 years, for example, then the grass needs sufficient rainfall to grow enough, and if it doesn't get it, it doesn't grow. And if it gets a lot, then you get a lot more biomass, and that's really reflected in the feature importances that we showed here, although there is a significant component of vegetation indices also included in the more important features. When you look at the Sentinel-2 model, though, really it's only one or two, well, there's only 4 features, I guess, but especially for the surface cover, about 50% of that was just observable in the red band. Now, I'm trying to, this work in general is something I've been sitting on a little bit since I started working here. I'm trying to breathe a little bit more life into it again, and this is something that I'm really keen to explore as to why it should be that so much information is contained within, in this case, the red band of a Sentinel-2 image, and what we can say then about biomass on the basis of this spectral information. But with this sort of double random forest map, you can create, in essence, biomass maps in any shape and size you want, as long as you've got the Sentinel-2 data for it, in this case, or other reflected data if you are training another model. An example here of Kafue National Park, where we did a lot of our work, showing how you can see like there's particular bands of where there's less grass cover, so this corresponds to higher tree cover. And yeah, if anyone's interested in using this data or using in particular the drone images, you can find them here at that link or scan the QR code. And with that, I'll let you get to your coffee, unless there are any questions. Thank you very much.
Hands, 2 at the front, I think the woman in the hat.
Yeah, so I saw that you used synthetic aperture radar, so I was just wondering if you had a trade-off with those data.
So I didn't use synthetic aperture radar. There was a mention of it in the context of more woody vegetation. We were specifically trying not to use it for this particular roof and surface level.
So, given that you've kind of come up with some relative feature importance and you can sort of model, where the biomass is and the climatic effects, could your data then be the basis for a predictive model to say kind of when next year's fires are most likely to be?
Ooh, I think it's tricky because we're relying on optical imagery, right? So unless I don't know of a way to predict the specific reflected or radiance values for something like a Sentinel-2. What is certainly true is if you could predict things like rainfall, then you could get a sense of where there might be higher fuel, so higher risk of wildfire in that sense. That would be the way I would approach it. I can't think of a way to do it directly.
Okay, I think we're going to stop there and finish on time. I'd like to thank all the speakers again. I'm sure they're all around in the coffee break, so you know who they are and come and harass them. But yeah, coffee break, half an hour, and then see you back here. Thanks, everybody.